Hello friends, so today we are going to solve questions that was asked in the year 2016, and for 2016 one question is from mains and one question is from advanced. So total there are two questions, and from the year 2017 we are having two questions from mains and one question from advanced. So total it is having three. So total there are 5 questions, and the first question which was asked in the year 2016 mains, and it states that two identical wires A and B, each of length L, carry the same current I, where Y is bent in a circle of radius R and wire B is bent to form a square of side L. If BA and BB are the values of the magnetic field at the center of the circle and square respectively, then the ratio of BA and BB will be. So here two wires, we have wire A, and that is a circle, and this circle is having, you can say, radius is R and current is I. Then we have a wire B which is in form of square, and the square is having a side length of small l, and current here also is I. Okay. And the length of the wire of A was capital L, and that of wire B it was also capital L. Okay. Therefore, for wire A, we get a circle. So we can say for circle, our length L will be equal to the circumference, that is 2 pi r, and this gives us that the radius of the circle will be equal to L upon 2 pi, and for square, this capital L will be equal to perimeter, and this gives us 4 times small l. So it means small l will be equal to capital L divided by 4. Now we are going to find out the magnetic field at the center of the circle as well as square. So first we are going to start with the circle. Magnetic field at the center of circle, and that is said to be BA. So we can say our BA will be equal to mu naught I upon 2r. We already know value of the radius, so we get this as mu naught I upon 2 L upon 2 pi, and here 2 goes with 2, so we are left with mu naught I pi divided by L. So this is the magnetic field at the center of the loop circle. Then we find out the magnetic field at the center of the square. magnetic field at the center of square. And we already know that is said to be BB, and we can write it as 2 square root 2 mu naught I upon pi L. We already know value of L, and we substitute it. We get this as 2 square root 2 mu naught I upon pi, and this becomes L upon 4, and this gives us 8 square root 2 mu naught I upon pi L. And even if you don't remember the formula for the, you can say, square, so this can be easily formulated. So if this is a square, and this is a center, so we can consider one of the side and find out the distance, because this is a finite wire, and suppose this is point P, and distance perpendicular of this finite wire from point P is suppose A, and we already know this formula. So this angle will be 45, this angle will be 45, so it comes as mu naught I upon 2r and 4r rather, sine phi 1 plus sine of phi 2. So we are going to get the same answer. And now it is simple finding out the ratio. So we can say our BA upon BB, we can write this as mu naught I pi upon L, and this comes 8 square root of 2 mu naught I upon pi L. And here this mu naught I, L and L goes away with this mu naught I, and this will be equal to pi square 8 square root by 2. And the option that are available with us is option number D is the correct option. So you can see option D is correct. We come to the next question, and that was asked in the year 2016 in advance, and it states that a rigid wire loop of square shape having side length L and resistor R is moving along x-axis with a constant velocity v0 in the plane of the paper. At t is equal to 0, the right edge of the loop entered a region of length 3L where there is uniform magnetic field B0 into the plane of the paper, as shown in the figure. For sufficiently large V0, the loop eventually crosses the region. Let x be the location of the right edge of the loop. Let Vx, Ix and Fx represent the velocity of the loop, current of the loop and force on the loop respectively. As a function of x, counterwise current is taken as positive. Which of the following schematic plot is or are correct? Ignore gravity. So we are given that this figure, and the magnetic field starts from 0 up till 3, and initially the loop is completely outside the magnetic field, then it comes inside the magnetic field, and finally it crosses the magnetic field. Therefore, we have to find out what will be the, you can say, our graph for force, velocity and current. Okay. So current are having two options, whereas force and velocity are having only one option. So this is basically multi-correct option, and for this case we have to see which of the options is or are matching with the given description. Okay. So we can divide into this entire discussion into three regions. So we can call this a region 1, region 2 as well as region 3. And for region 1, which is basically our x is less than 0, and for region 2 that is between 0 and 3L, and region 3 is greater than 3L or just at the edge of 3L. Okay. So let's call this as first region as entering the magnetic field. Entering the magnetic field. So we can find out the induced EMF as well as induced current. We can say that induced EMF will be equal to minus d phi upon dt. We can substitute formula for the phi, that is of flux. We get this as minus d upon dt, and this comes as b naught L multiplied by x and divided by dt, and this gives us that induced EMF will be equal to, this will be minus dx upon dt, which is nothing but our velocity. So we can write this as minus b naught L velocity v naught. So this is our induced EMF, and because of this there will be induced current. So we can write induced current that is our Ix will be equal to induced EMF divided by resistance R, which gives us minus b naught L Vx upon R. Then we are going to find out now the magnetic force. Magnetic force, which is our f of x, will be equal to our current I of x L, and we have this as b naught. So we already know our I of x, we substitute it, we get this as minus, this will be our b naught square, and we have here L square Vx divided by R. And the direction of this force will be towards left, because you can say it is going to oppose the motion of the loop, which is towards the right. So you can say that direction of Fx is toward left. Now we can find out our acceleration. So acceleration will be our A of x, this will be our force, magnetic force, divided by m, and we already know this will be minus, and we get this as b naught square L square V of x times R. And from here we can say that, okay, now here this acceleration is basically negative, or we can also call this as a retardation. So it means the velocity of the loop decreases as it enters the magnetic field. You can say that velocity of loop decreases as it enters the magnetic field. And we can further solve it. We can write that our acceleration A, which can be written as, you can say, v dv by dx, and this will be equal to minus, we have this as b naught square L square v of x, and divide by mass into r. Yeah, here has to be mass also. And we can just modify it, and this can be written as dv will be equal to minus b naught L square divided by mr, and this gives us dx. We can find out for the entire region. So it starts with v naught to a velocity v, and distance vary from 0 to x. Therefore, we can write that our v is equal to v naught minus, this comes as b naught L square v of x, and mr multiplied by x. And these two terms should be also dependent upon x. So v of x, v naught of x. And for the sake of convenience, let us say here it will be only x. And for the sake of convenience, let us assume that this particular function, that is our b naught square L square divided by mr, is a constant k. So we can write that our v of x will be equal to v naught of x minus k times x. And similarly, we can write for the current also. We can say similarly our I of x will be equal to, we already have this as v of x b naught L upon r. We substitute value of v of x, and v of x is our v naught x minus, and we were having here b naught square L square mr times x, and multiply by b naught L upon r. So therefore, our current I of x will be equal to v naught x magnetic field L r minus, this comes as b naught cube, and our L cube mr square times x. Now if we put value of x equals 0 in both these equations, let us call this as 1, this as equation 2. So for x equals 0 in equation 1 and 2, we get I of x will be equal to V naught x B naught L divided by R, and this is nothing but maximum, and our V of x will be equal to V naught x, and this will be also maximum. So in this case, now the loop is approximately here. Okay. Entire loop is inside, and now we have to find out for the second region, and we can say inside the magnetic field, or we can say x is greater than L but less than 2L. So within this region, the loop will be entirely, or we can say completely, inside the magnetic field. The loop is completely inside the magnetic field. So which basically means that flux becomes constant, because the area with respect to field is not changing at all. So we can say flux becomes constant as the area inside the magnetic field no longer changes. So therefore, we can say the induced EMF will be 0, the induced current will be also 0, the force will be also 0, and the velocity is going to remain constant. Velocity remains constant, that is our V of x will be now our V of L, because it is entirely in magnetic field, and magnetic field as such does no work on the moving coil. Now we come to the last region, that is exiting the magnetic field. Exiting the magnetic field. And this is for when x is greater than 2L but less than 3L. So now once again there will be induced EMF, and the loop exits, the magnetic flux is going to decrease. Okay. So we can say as loop exits, magnetic flux decreases. Therefore, we can write induced EMF minus d phi by dt. This gives us B naught L and V of X. Based on this, we can find out the current, that is of I of X, and that will be equal to, rather we can say induced current. So we get this as B naught L V of X divided by resistance R. And now we have the magnetic force, that is our F of X will be equal to IXL B naught. So this gives us B naught square, and we have it L square V of X divided by R. Now once again we can find out the acceleration. So we can say our acceleration A of X will be equal to F of X divided by mass. So this gives us B naught square L square V of X. Now it comes as mR. And this force will be now in the left direction. And we can further solve it. Once again, similarly in the first part, we wrote it as V dV by dx. This gives us B naught square L square V of X mR, and this can be written as B naught square L square, and here we have mR. This comes at dx, and this is our dV, and we integrate. It goes from L to X, and it goes from our Vi to V. Therefore, we can write that this V of X will be equal to Vi of X minus, we get this as B naught square L square mR, and this is X minus L. So this is basically nothing but a straight line equation with negative slope. Straight line, negative slope. So let us summarize and the entire thing, and the options that are with us, we can clearly see that the magnetic field, let us start with the we can say velocity first of all. So velocity first decreases, then it becomes constant, and it decreases. This option is the correct one. And for the current, we can clearly see that the current will be first in one direction, like in said that counterclockwise is taken as positive, then it is going to turn to the clockwise direction. Okay, so this option, both the clockwise and counterclockwise, it is saying it will be a positive one. So this option is wrong. So current is our option number B is the correct one. And the force, if you see the force, the direction doesn't change, so it remains at the, you can say, same. So this is not the graph for force. So option B and C are the correct one. Option B and C are correct. Come to the next question. Now this one was asked in the year 2017 mains, and it states that A magnetic needle of magnetic moment 6.5 into 10 to the minus 2 ampere per meter and moment of inertia 7.5 into 10 to the minus 6 kg meter square is performing a simple harmonic motion in a magnetic field of 0.01 Tesla. Time taken for the complete oscillation is. So in this case, we are given that the body is providing a simple harmonic motion, okay, and that is a magnetic needle. Okay. So for case of, you can say, simple harmonic motion, the magnetic needle in the uniform magnetic field will be experiencing some kind of restoring torque when it will be displaced from its equilibrium position, and this torque is going to result in the oscillation, which we can call it a simple harmonic, and that you can say displacement from the equilibrium position has to be very small. So we can derive the time period of oscillation. Time period of oscillation, and the torque acting on the needle, that we can say torque will be equal to minus mb sine of theta, and for small oscillation we can say our sine of theta is approximately equal to theta. Therefore we can write that our torque will be equal to mb times theta. Okay. Now this torque is going to produce a angular acceleration. Say this torque produces angular acceleration. So we can write the torque is equal to moment of inertia, angular acceleration, and that will be equal to our I d square theta divided by dt. Therefore, we can write it further as I double derivative of theta is equal to our minus mb times theta, and this gives us an equation that is a differential equation for our SHM, and this will be plus mb divided by I times theta is equal to 0. So we can say this equation is, or we can say this is differential equation of SHM. This is differential equation for SHM with the angular velocity that is at omega will be equal to square root of mb square root of mb divided by I. So now we can find out easily the time period. Time period t will be about 2 pi by omega, and this gives us 2 pi square root of I upon mb. Now we are going to simply substitute the values. We get this as our t is equal to 2 pi square root, we have this is 7.5 into 10 to the power minus 6, 6.7 into 10 to the power minus 2, and this is 0.01. So time period is approximately equal to our 0.665 seconds. And we need for 10 oscillations. Okay, so you can say for 10 oscillations, for 10 oscillations, total time is equal to 10 times t, which gives us 6.65 seconds. So option number D is the correct option. Option D is correct. Now we come to the next question, and that was also asked in the year 2017 mains, and it states that a uniform magnetic field B exists in the region between x equal to 0 and x equal to 3r/2, that is region 2 in the figure, pointing normally into the plane of the paper. A particle with charge plus q and momentum p directed along x-axis enter the region 2 from region 1 at a point y is equal to p1, y is equal to minus r. Which of the following option is or are correct? So we are given this figure, and it says that plus q enters a point p1, and it's, you can say, the coordinate is given as y is equal to minus r, and magnetic field which is pointing in the downward direction. So first of all, we are going to find out which of this option is the correct one. So here, as soon as it enters the magnetic field, this positive charge is going to follow a circular path. We can say that magnetic force which is of F Q VB causes the particle to move in a circular path. And we can say the radius of which if it is written as capital R will be equal to, we can write in the form momentum, because momentum is given to us, that is about P divided by Q times B. Now we are given the boundary condition, and the boundary condition is that when x is less than 0, magnetic field is 0. Between x0 and x3r/2, we have a magnetic field that is of a B, and for x greater than 3r/2, the magnetic field is once again 0. So both sides, left and right of the region, the magnetic field is 0. So in these cases, the charge can complete, you can say, re-enter the region of the magnetic field again, or we can re-enter the region 1 again by moving in the magnetic field, or it can simply cross into region 3. Okay, so let us call this a region 1 we have region 2 and this is region 3. Okay. So there are two possibilities. Particle can again, or we can charge again, come back to region 1, or it can move into region 3. That depends upon our magnetic field. So let us find out what will be the trajectory of the particle, or we can say charge, in the region 2. Trajectory in region 2. Now it says that the particle enters at P1. Particle enters at P1 and whose coordinates is given as 0 and minus r, and along x-axis. Along x-axis, and so radius we already know, that is our radius is our momentum divided by charge multiplied by magnetic field. So therefore we can say the center of circular path it will be at 0 minus r plus r. So therefore it is going to move something like this, and the center, so center will be, this will be suppose minus r, and this is our r, so therefore center will be minus r and plus r. So center will be somewhere here, and so it means center lies at a distance, one second, I think I have to, this is, yeah, so we are given that radius is, one second, yeah, so radius, so we have this radius is our small r. So this will be the radius of circular path, and the charge is entering from here. This is our minus r, and it will be going in this direction. Okay, and this will be the small r. And yeah, now it's okay, and we are given that, first of all let's check the option. It states that when the particle re-enter region 1 through the longest possible path in region 2, the magnitude of the change of linear momentum between point P1 and the farthest point from y axis is p by 2. So we are going to find out the change in momentum. So first of all let's find out what will be the condition for re-entering region 1. Condition for re-entering region 1. Under this condition, or we can say the condition is that the radius must be small enough that the particle does not exit. So it means the value of radius should be smaller than this particular value. So we can say that radius r must be small, that is less than 3r/2. And for critical condition, we can say that the particle or charge just grazes the boundary x is equal to 3r/2. Say the critical condition occurs when the particle just grazes x is equal to 3r/2. So it means maximum horizontal distance it can travel is r. So we can say that maximum horizontal distance traveled will be equal to the radius. And for re-entry, this r should be less than 3r/2 for re-entry into region 1. The value of r, that is radius, should be less than 3r/2. We already know the value of small r, therefore we can say that P/QB should be less than 3r/2. So this gives us that our magnetic field should be greater than 2p 3q times r. So let me check what, 2/3. So option number C is correct one. Okay. For condition of re-enter. Okay. Option 3 is correct. 3 is correct. Now, when it says the condition to enter region 3 at P2, condition to enter region 3 at P2. So it means the particle should be exiting region 2 into region 3. Okay, and here the particle, or we can say P2, is exactly on the x-axis. Okay, so you can say, you can draw a rough approximate for that, and we have this as a x-axis, and the particle start from here, that is our minus r, and this is our point P2. So the particle should be exiting somewhere here. Okay, so this is our x-axis. So you can say for particle to enter region 3 at P2, on x-axis, the circular path must pass through the circular path must pass through 3r/2 and 0, because this is our x equal to 0 and this is our x equal to 3r/2. So this particular point we can write it as 3r/2 and 0. And we know that the center of circle we already know. Center of circle, that is our 0 minus r plus r. So we can find out the distance of center of to point P, and that should be actually the radius of the circle. So we can say the distance from center to P2, we can use the distance formula, and we are going to get as 3r/2 whole square plus r minus r whole square square root should be equal to the radius. And if we solve it, we are going to get our small r will be equal to 13r/8, and small r we already know is P/QB. So we substitute it, we get P/QB will be equal to 13/8 multiplied by r. So this gives us our magnetic field B should be equal to 8/13 P divided by QR. So let us check. Yeah, so option number B is the correct option. Option B is correct. Now we can find out the change in momentum. Change in momentum. So initial momentum was along our y-axis, and that is, you can say, for returning back into the region 1. Okay, I think that was the, yeah, re-enter region 1. We have to find out the change in momentum. Change in momentum. So it means the particle will be only for half circle. Therefore, you can say that when the particle enters region 1 after half circle, after half circle. So our initial momentum that is our Pi, initial momentum at P1 is our Pi, and that we can write our I unit vector, and the final momentum let us call that as Pf, which will equal to minus of Pi, because now it is going to complete, initially it is in this direction I, so it is going to complete half circle and come back into its region. So only the direction of the momentum is going to change initially is equal to pi, and finally it will be equal to minus of pi, because the velocity is going to remain same and mass is also not changing. Therefore, we can find out the change in momentum. Change in momentum, that is our delta P will be Pf minus P initial, and obviously that will be giving us only magnitude we are interested, that will be equal to our 2P. So the option that is given to us, it contains P by square root of 2. So this is incorrect, so option A is incorrect. Let's say option A is incorrect. And finally, we come to the final option, that is option number D, and here the distance of the point P and re-entry depends upon the radius. Say the distance between P and re-entry point depends on radius, and that radius is our P divided by QB, and both our, or we can also say it is a MV divided by QB. So for fixed value of our velocity, mass and magnetic field, we can write that our radius is directly proportional to mass m. So it means it is proportional to direct relationship, and the option that in the D option that is mentioned, that it is inversely proportional to the mass of the particle. Okay, so this option is also incorrect. You can say option D is incorrect. Is incorrect. And now we come to the next question that was asked for the advance 2017, and the question states that a charged particle, electron or proton, is introduced at a origin x equal to 0, y is equal to 0 and z equal to 0 with a given initial velocity v. A uniform electric field E and uniform magnetic field B exist everywhere. The velocity v, electric field E and magnetic field B are given in columns 1, 2 and 3 respectively. The quantities E0, B0 are positive in magnitude. So we have 3 columns, 1, 2 and 3, and the first it says, and we have 2 particles. One is of electron and another one is a proton. So we have 2 things that are associated with electron and 2 things that are associated with proton. So column 1 gives us about the velocity, column 2 gives about the electric field, and column 3 gives about the magnetic field. So based on this table, we have 3 questions, A, B and C, and we have to find out the perfect match between the column 1, column 2 and column 3. In first case, it says that in which case would the particle move in a straight line along the negative direction y-axis, that is move along minus y unit vector. So it means basically the particle should be moving in a straight line. We start with option A, part A. which wants that particle moving straight line, and here particle means electron or it can be proton. So particle moves in straight line, and the straight line is along y unit vector, okay, or we can say y axis, negative y axis rather. So we know that when a particle, electron or proton, it moves in electric field or magnetic field, there will be two forces acting on it. One will be because of electric field, that is QE, and another one will be because of the magnetic field, that is a QV cross B. So we are going to take the options one by one and try to find out which one matches the given option, that is a line should be straight line in minus y or minus y axis. Okay. So let us start with option A. In option A, it gives us that the fourth option matches with second option. Sorry, let me write it correctly. So it gives us that we have fourth option, it matches with second one, and it matches with the alphabet S. So first, the particle is of a proton. So particle is proton. So basically, which means charge is our plus E, and the velocity it is given as V, and it is about 2 E naught upon B naught, and that is in X direction, and our electric field, that is our E, is along minus y direction, and we have magnetic field B, that is along our positive Z direction. So first of all, let's find out what will be our electric force. So our electric force will be our Q multiplied by electric field, and Q is our positive, so this is our plus E, and this is minus E naught, and we have y unit vector. So we get our electric field is equal to minus E naught, sorry, minus not minus E naught, but minus of E naught, and here we have y unit vector. So this is the force on the electric field. Now we find out the force because of the magnetic field, and for that, first of all, we need to find out V cross B. So we find out V cross B. V is our 2 E naught, B naught, and is our X unit vector cross. We have this as B naught Z unit vector. So this is basically our X cross Z, and X cross Z will be giving us minus of Y, and here B naught and B naught cancels out, so we get the cross product will be equal to minus 2 E naught, and here we have a Y unit vector. So therefore total force that is F will be equal to Q electric field, and we have here V cross B, and we can know that we know already the charge electric field just we found out is minus E naught Y unit vector, and this is minus 2 E naught y unit vector. So this is the force F will be equal to, we come this as minus 3E and E naught, and we have this as y unit vector. So this will be a force on the the charge, that in this case is our proton, and therefore we can also find out our acceleration, and acceleration will be our force oblique mass, and this gives us minus 3E E naught divided by mass m y unit vector. So obviously it is along our minus y axis, and the initial velocity is along plus y. The initial velocity is our v, which is our 2E naught b naught x unit vector, and this is in plus x axis. Okay, so it means this is, we can say, not in our minus y axis, not in minus y axis. So it means there is a change in direction, or we can say curved path is being followed. So this option is incorrect. Option is incorrect. Let us come to option B. Option B gives us, we have second, matches with our third, and the alphabet is given as Q. Now in this case the particle is electron. So we have our electron. So therefore the charge will be our minus of Q. Velocity V, it is given as E naught b naught y unit vector, and we have electric field, that is E naught x unit vector, and we have magnetic field, that is our electric field, magnetic field is our b naught x unit vector. So let's find out of the force because of electric field. This gives us minus of E, and this we have minus E naught x unit vector. So this gives us the force due to electric field is equal to our E naught, and we have x unit vector. Similarly, we find out magnetic field force, that is FB, and for that we are mainly interested in the cross product because that is going to give us the direction. So we get this as E naught upon B naught y unit vector cross, and magnetic field is along our x axis, so B naught x unit vector, B naught and B naught cancels out, and we get here y cross x cross, and this gives us our E naught will be equal to y unit, and x unit gives us a z unit. Therefore the total force F is equal to, we have charge is our minus E, our electric field is, force is E naught x unit vector, sorry, yeah, we can just solve it, it will become the same, and we have this as plus E naught z unit vector. So this gives us E naught x unit vector minus E b naught z unit vector, and we can find out our acceleration also. Acceleration will be equal to force oblique mass, and force is our E naught x unit vector minus E B naught Z unit vector divided by mass. And we can also say from here that our acceleration is directly proportional to our E naught x unit minus E B naught Z unit. So the acceleration has both x component as well as Z component. Okay. And none of the component we can say that Y unit vector is missing or Y unit component is missing. And the initial velocity that is our V, it is given as E naught B naught Y unit vector. So obviously that is along plus Y and not minus Y. This option is also incorrect. This is incorrect. Now we come to the option C. Option C gives us that our third matches with second and the alphabet is our R. So here once again it is a proton. So we can say, yeah, so it is proton, so giving us plus E, velocity is given as 0, electric field is minus E naught Y unit, and magnetic field is given as B naught Y unit. So we can write out our electric force will be equal to E minus E naught Y unit, and this gives us the electric force will be equal to minus E naught Y unit. And for magnetic force we are mainly interested in cross product, but velocity is equal to 0. Okay, so we can say V cross B is equal to 0. So therefore total force will be equal to FP will be equal to 0. So the force, that is our total force, will be equal to minus E naught Y unit vector. Okay. And initial velocity is given as V is equal to 0. So we are given that our initial velocity V is equal to 0. So it means particle starts at origin and the only force that is acting on this particle is our electric force. So you can say the particle starts at origin and force F acts along minus Y unit vector. So therefore particle will move in straight line along minus Y, or we can say negative Y axis. So therefore this option is correct. this option is correct. So it means option number C is our correct option. Now let us check option D. Option D states third matches with second and it matches with alphabet P. And here once again we have proton that is equal to plus E, and the velocity V is still equal to 0. Electric field is our minus E naught y unit vector, and our magnetic field is minus B naught, and we have x unit vector. So magnetic force, or we can say electric force, will be equal to minus E and E naught y unit vector, and initially the magnetic force will be equal to 0. You can say initially magnetic force is equal to 0. But as particles start, so at the start, or we can say at the start, the only force will be acting along minus y direction. You can say from here that initial force is along minus unit vector. So therefore particle starts to move in minus y direction. But now it is going to start gaining some speed. It means now the velocity will not be equal to 0. So we can say that but now it gains speed, and we can write our velocity will be now in a y direction, and now the magnetic field will come into the picture. Okay, or we can say magnetic force will come into the picture. Therefore magnetic force kicks in, and we are interested in y cross x, which is our z. Okay, so we can say our magnetic force will be equal to charge minus y unit vector cross minus our x unit vector. So this gives us E velocity, and that velocity is in y direction, and we get this as B naught and z unit vector. So magnetic force has now a component of a plus z. Magnetic force now has plus z component unit vector, and no the y1. So the particle still continues to move in minus y direction, but slightly curves into z direction. So we can say that the particle curves into z direction. So it means this is also incorrect. This is not correct. Now we come to the part B, and in part B it says that the particle moves in a straight line with a constant velocity. So once again we are going to make analysis for all the given options. So we have our part B will state that particle moves in a straight line with constant velocity. Particle moves in straight line with constant velocity. And for straight line, you can say that our V cross B, or we can say the force should be equal to 0, or V cross B should be equal to minus of E. So for this total force, that is F, which is our Q, E V cross B, and this should be equal to 0. So it gives us that our V cross B should be equal to minus of E. So then the particle will be moving in a straight line with a constant velocity. So we have option A. And option A, it gives us that the second matches with third option, matches with alphabet S. And we have electron, minus of E, and our velocity is given as E naught, B naught, Y unit vector. Electric field is minus E, is E naught, X unit vector minus, and we have magnetic field is our B naught times Z unit vector. Once again we can find out, let's find out first of all V cross B. V cross B will be our E naught, B naught, Y unit vector cross B naught, Z unit vector, and this gives us B naught and B naught cancels out. So we have our Y unit vector Z cross Z unit vector. This gives us E naught, X unit vector. And our electric force, that is a Fe, will be equal to minus of E and plus this will be E naught and our X unit vector. Therefore total force F will be equal to, we have minus of E minus E naught X unit vector plus E naught X unit vector. This comes as 0. So it means our acceleration will be equal to 0. So this means velocity is constant. So this option is correct. This option is correct. Similarly, we come to the option B. Option B gives us that option gives us that we have a third matches with option third, and alphabet is P. And here we have a proton, velocity v is 0, electric field is minus E naught x unit vector, magnetic field is minus B naught x unit vector. So first of all, let us find out our V cross B, which is 0, and our electric force will be our, we have proton, so this comes as plus E, and minus this will be E naught x unit vector, and our total force, that is F, will be equal to force due to electric field plus force due to magnetic field, and the magnetic force, that's the FP, is our 0. Therefore we can say that total force F will be our minus E naught x unit vector, which is not equal to 0. Therefore velocity is, or we can say acceleration, the particle accelerates, therefore velocity is not constant. Velocity is not constant. So this option is incorrect. So for option part B, option A is correct. This option is correct. Now let's check option C. Which gives us that we have fourth option matching with first option, and alphabet is S. Here we have a proton, that is plus E, velocity is 2 E naught upon B naught x unit vector. We have an electric field, that is our E naught Z unit vector, and magnetic field is our B naught and Z. So once again we are going to find out first of all our V cross B. So V cross B, it gives us 2 E naught B naught x unit vector cross B naught Z unit vector. So this comes as twice E naught minus of Y unit vector. So therefore force, and we can say our electric force Fe will be equal to our E multiplied by E naught and Z unit vector. And from here also we can see our cross product is not equal to 0. So neither magnetic field is equal to 0 nor our electric field is equal to 0. So therefore the total force will not be also equal to 0, because it will be simple addition. So this option is also incorrect. So force is not 0, so velocity is not constant. Velocity is not constant. This option is incorrect. Now we find out for option D. For option D, we have third matches with second, and alphabet is R. Here we are given as proton, that is our plus E, velocity is 0, electric field is minus E naught y unit vector, magnetic field is B naught y unit vector. So electric force Fe will be equal to our minus E naught y unit vector, and our V cross B will be 0. So this gives us our magnetic force will be equal to 0. Therefore the total force F, which is our Fe plus Fp, will also be not equal to 0. Therefore particle accelerates. Particle accelerate, velocity is not constant. Now we come to its part C. And here it says that particle describes helical path with axis along positive z direction. We have helical path with axis along positive z direction. And for helical path, we know that the velocity component parallel to z, or we can say helical path for specifically for positive z axis, it is required that the velocity component parallel to z should remain constant, that there should be no acceleration, and the magnetic field component along z that is going to cause a circular motion should be our causing the circular motion in xy plane due to the velocity component perpendicular to z. So let us find out. The component will be associated with the velocity. One will be perpendicular, another will be the parallel, and the axis should be, helical path axis should be our plus z. So we start with option A. And option A gives us that the second should match with second, and it should be our with R. And here we have charge as electron, minus E, velocity is our E naught upon B naught y unit vector, electric field is minus E naught y unit vector, and we have a magnetic field that is our B naught is also in y unit vector. So first of all we have to check the magnetic field. So you can say magnetic field that is our B is our B naught y unit vector, and this is which is along y unit and not z unit. Okay. So it means the helical axis cannot be along z direction. So helical axis cannot be along z axis. Now we come to the option B, and it says that third match it with third, and the alphabet is our P. Here we have a proton plus E, velocity is 0, electric field is minus E naught x unit vector, and magnetic field is our b naught x unit vector. And here also magnetic field is along, not along z unit, straightforward. Magnetic field is not along z. Okay. And the particle is going to accelerate in the x unit direction, and because the initial velocity is 0, so there will be no helical motion, or we can say it doesn't have anything that relates with z unit vector. You can say this option is incorrect. Option is incorrect. Now we come to option C. And option C gives us that the fourth matches the first, and alpha beta is given as S. So here we have a proton, that is our plus E. Velocity is twice E naught B naught x unit vector. Electric field is our z unit vector, and magnetic field is our z unit vector. So it means the magnetic field is along z axis, so it satisfies the initial condition for helical axis. You can say that magnetic field satisfies the condition for helical axis. Now let's make a final analysis. For that, we are interested in V cross B, and V cross B gives us twice E naught B naught x unit vector cross B naught z unit vector, and this comes as twice unit twice E unit y unit vector minus. So it means this is going to cause a circular motion in xy plane. This results in circular motion in xy plane. And our electric field, that is of Fe, is our E naught z unit vector. So therefore we can write our acceleration will be equal to E naught divided by m, and that is our z unit vector, so which is, it is going to accelerate along positive z with increasing velocity. Accelerate along positive z axis with increasing velocity. With increasing velocity. So it means the motion is helix along plus z. Okay. So means this option is correct, or we can say this is our helix motion along plus z. So C option is correct. And finally, let's check our option number D. And here we have a proton. Option D gives us that fourth should match with second, and the alphabet is our R. So here we have charge as proton, that is our plus E. Velocity is our twice E naught, B naught over x unit vector. Electric field is our minus E naught y unit vector. Magnetic field is our B naught y unit vector. And once again, magnetic field is not along Z. Magnetic field is not along Z. So means this option is incorrect. Therefore, the option number C for this last part is correct. So this completes all the questions from 2016 mains and advanced and 2017 mains and advanced. Thank you.